Okay, in the previous video, we looked at different ways that we can combine vectors in R2. Combine by, I mean add different scalar multiples of vectors in R2 to wind up with a specified vector. And so we can do this in general in higher dimensions. So let's say I have p different vectors that are all n-dimensional. So v1 consists of n numbers, v2 is a column vector of n numbers, and we have p different vectors, each of which contain n different numbers. And we want to think about, is there a way that I can add some scalar multiple of these vectors v1 up to vp and wind up with some specified vector y, which also sits in Rn. And so we say that if this can be done, then we say that this vector y is a linear combination of the vectors v1 up to vp with weights that are given by c1 up to, that should be a p over there, up to c sub p. So each of these c's is a scalar, each of these v's is a given vector, and we're taking some linear combination of these to wind up with the vector y. So this is a really important key definition in linear algebra, which is what is a linear combination of vectors. So for example, we worked in the previous video with these vectors 2, 1, and minus 1, 1. And we thought about, the picture here is that we can think about a city which lives in R2, and we have a grid system of streets. Some of the streets run parallel to 2, 1, and the other streets run parallel to minus 1, 1. And so if I'm only allowed to walk in these directions, how could I wind up, let's say, at some other vector, which is, in this case, 2, minus 3. So I've marked that down here with this black point over here. And we could solve a matrix equation like we did in the previous video, and we can see that if I go minus 1/3 in the direction of 2, 1, and then minus 8/3 in the direction minus 1, 1, yes, we would wind up perfectly at this point. So given any point in R2, we can find some combination of 2, 1 and minus 1, 1 that's going to put us at that point. So here's a question to think about before moving on to the next slide, is that can you think of two different vectors in R2 such that taking some linear combination of those vectors, we wouldn't be able to arrive at 2, minus 3? So give this question some thought, and if you have some trouble, you're not able to figure this out, hopefully some of the examples we're going to take a look at next will help you clarify your thinking on this question. Okay, so now that we know what a linear combination of vectors would be, let's define what the sets spanned by these vectors are. So if I have a collection, again, of v1, v2 up to vp, and these are all vectors in Rn. So we have p different vectors, and each vector has n different values in it. Then the set of all linear combinations of these vectors is called the subset of Rn, which is spanned by vectors v1, v2, v3, all the way up to v sub p. And so we would denote, this is a set of vectors, so we denote this set of vectors with the notation span, and then in curly braces, the vectors v1 up to vp. So a very typical question in linear algebra would be, is a certain vector in the span of a certain set of vectors? So is the vector y in the span of the set of vectors of v1, v2 up to vp? And this question, to try and answer this question, recall we can frame this in terms of a system of linear equations. So can I find some scalar c1 that I multiply by the vector v1 and then add some linear combination of the other vectors? Is it possible to wind up with y in the end? So if this system of equations has a solution, then yes, y would be in that span. If this system of equations does not have a solution, then y would not be in that span. So in other words, what we have is an augmented matrix where column 1 in this augmented matrix is going to be the vector v1. So this is a whole column. Column 2 is v2, all the way out, and then our very last column is going to be the vector y that we're trying to determine whether or not that's in the span. So we will take a look at some special examples on the next couple of slides.